Alright, so now we'll solve this question. You can see this is the problem. We need to calculate the heat loss from a steam pipe in windy air. So you can see this picture here. This is a long steam pipe with 10 centimeter diameter, and the surface temperature is given 110 degrees centigrade. So it is, you see, 110 degrees centigrade. It is passes through the some open area that is not protected against the winds. We need to determine the rate of heat loss from the pipe per unit of its length when the air is 1 atm and 10 degrees centigrade temperature. And the air velocity is given 8 meters per second. So if you look at the image here, everything is given. You see the velocity, the air temperature 10 degrees centigrade, the diameter of the pipe, and the surface temperature of the pipe. So when it is if we cannot just understand actually the heat transfer mechanism here, it's really convection. And we know the surface temperature, and we know the air temperature, the ambient temperature. So we need to use the Newton's law of cooling. So now what we will do, we will go to, now we will solve this question. So what we usually do to solve some heat loss by using Newton's law of cooling is we know the formula. Like if it is heat transfer, let's say Q equal Hs A delta T. So it is Hs A. So the temperature difference, let's say surface temperature and the air temperature. So the surface temperature, this temperature difference will always be from positive to negative, or high temperature to lower temperature. So you know that. And now from here, this is our ultimate target Q. So to get this, we actually need to use this formula. So the temperature difference that we know, and now what else we need? We need the surface area. So area, we know it is equal, actually when it is a circular pipe, so let's say it is pi dl. Then we need the Hs, the heat transfer coefficient. So heat transfer coefficient, it is actually the function of Nusselt number, isn't it? It is function of Nusselt number. So now once we need the Nusselt number, we usually know Nusselt number. If we want to select the correlation for Nusselt number, we need to find out the Reynolds number. So that's important. We need to check whether the flow is laminar or turbulent, or depending on the Reynolds number, we actually have different Nusselt number correlations. So that's actually the total or the flow chart we need to follow. So that means at first we need to calculate the Reynolds number, then we will calculate the Nusselt number. Once we have the Nusselt number, then we will have the Hs, then we will calculate the area, and finally we will get the the rate of heat loss. So before calculating the Reynolds number, we actually need the properties, right? We need the properties. So that's actually the total flows that we're going to follow. So in this question, we have this long, say, stream pipe, and we know the surface temperature is 110 degrees centigrade, and the velocity, the let's say the air velocity, it is equal 8 meters per second, and the temperature, the atmospheric temperature T infinity equal 10 degrees centigrade. Okay. So now let's calculate the rate of heat loss. So at first, as usual, what we do, we need to write down the assumptions. So we can say that this is a steady operating conditions exist here. So I will not write everything. So a steady operating condition. A steady operating condition. And the second thing is, we will not consider the radiation heat loss. So let's say the radiation heat loss negligible. So that's two assumptions, and the other thing we can say that the properties are constant. The properties are constant. Alright, so once we have this, now we need to calculate the properties. So far you have solved many problems for heat transfer and you know how to calculate the properties. In this case, we have the pipe, the stream pipe, and we know the air temperature, atmospheric temperature, and the surface temperature. So when we will calculate the properties, we need to calculate the film temperature. So here, what will be the film temperature? So the film temperature TAP, it is equal the surface temperature, atmospheric temperature 2. So this is 110 and this is 10 over 2. So this is 60 degrees centigrade. So that means at 60 degrees centigrade temperature, we need to calculate the properties of the air. So this is actually the table A15 from your appendix. This is the the 5th edition is the unit book, so you can get all the properties from table A15. So what sort of values actually we need? We need the thermal conductivity. So thermal conductivity at 60 degrees centigrade, it is 0.02808. So watt per meter Kelvin. What other thing we need? We need the Prandtl number. So Prandtl number is 0.7202. And we can calculate the kinematic viscosity. It is 1.896 and 10 to the power minus 5 meter square second. So now we have all the properties. So once we got all the properties, then we can start with the analysis. So if you can remember, guys, when we will start with the analysis, the first thing we need to do is we need to calculate the Reynolds number. So then let's calculate the Reynolds number. So the Reynolds number here, we know the formula. This is we're using every time the velocity. Here we got, this is the pipe, so we know the diameter. Okay, we know the diameter, so we will use the diameter and the kinematic viscosity. So the velocity is 8 meter per second and the diameter is 0.1 meter. It was if you see here, the diameter it is given, and if you read the question, it is given there. So it was given 10 centimeters, so we converted it into meter. So it's 0.1 meter, and the kinematic viscosity, it is 1.896 and 10 to the power minus 5. So we'll get the Reynolds number is 4.219 and 10 to the power 4. So this is our Reynolds number, 4.219 and 10 to the power 4. So we already know different correlations for the Nusselt number, especially depending on the Reynolds number, we can use different correlations. But for this problem, you already know we have different correlations for Nusselt numbers. So here we are going to use the complex Nusselt number correlations, which is proposed by Churchill and Bernstein. So Churchill in 1977, he just proposed this Nusselt number correlation. It is equal, Nusselt number, it is equal 0.3 plus 0.62, the Reynolds number power half Prandtl number 1 over 3 over 1 plus 0.4 over Prandtl number, and the power is 2 over 3 and the whole power is 1 over 4 into 1 plus the Reynolds number over 282,000. It is 5 over 8 and the whole power is 4 over 5. So that's the complex correlations we got from Churchill's, and this we are going to use this correlation. You can use a simple correlations, still you will get some results, but maybe it is only the issue of the accuracy, that's it. But otherwise you can use other correlations, but we actually want to use some complex correlations, and because of the accuracy of the solution. So now we know every values, guys. You look here, now we know the Reynolds number, we know the Prandtl number. We only need these two values. So once we got this Reynolds number, so let's substitute the values for Reynolds number. So it is 0.62, and the Reynolds number we know 4.219 and 10 to the power 4. This is 4 half, and the Prandtl number, you know, it is 0.7202, 1 over 3. It is 1 plus, 0.4 Prandtl number is 0.7202, 2 over 3 power 1 over 4. And let's say we can write it down here. 1 plus Reynolds number is 4.219 to the power 4 over 282,000. This whole power is 5 over 8 and then 4 over 5. It's a bit complex. So you can use your calculator, and then we will get the value is 124, the Nusselt number. So that means we have the Nusselt number 124, and we all know Nusselt number is the function of, we know the general definition of Nusselt number is Hayes D, and the thermal conductivity K. So we actually need Hayes, so we can write Hayes equal Nusselt number into thermal conductivity over diameter. So the Nusselt number is 124, and the thermal conductivity we know 0.02808, and the diameter is 0.1. So if we solve this, we'll get Hayes equal 34.8 watt per meter square Kelvin. So we're almost done with this solution. We got the Hayes, the heat transfer coefficient. So once we have the heat transfer coefficient, then look at the flow charts, and then we'll see we already have the Nusselt number, we already have the Hayes. Now we need the surface area, the area, because from Newton's law of cooling we need the area A. So now calculate the area. Area, this is a pipe, circular pipe. It's the diameter is given, so definitely it is pi dl. So pi, we know the constant value d is 0.1, and length, it is for 1 meter. Because in the question it is given, you need to calculate the heat loss from the pipe per unit of its length. So length L equal here 1. And then we got the area is 0.3 on 4 meters square. All right, so we got it is 0.3 on 4 meters square. So that's the area. So now we have everything. What we can do now, the rate of heat loss from the Newton's law of cooling is Hayes. A is surface area, and the temperature difference. Here surface temperature is higher, so we will write the surface temperature at first. So Hayes equal 34.8, and the area is 0.3 on 4, and the surface temperature is 110, and this is 10 degrees centigrade. So we'll get the rate of heat loss is 1093 watt. So this Q is 1093 watt. Alright, so we got the rate of heat loss. If you want to calculate, this is actually for per unit length. If you want to calculate the rate of heat loss for the entire pipe, you can just multiply the value with the whole length. Anyway, just not the part of this question. But now the question is, here we have used you see the complex correlations for the Nusselt number. So what will happen if you use a simple correlations? So if you use the simple correlations from the table 7.1, you can see we have a table 7.1 from our book. So if you use this table, then we did some simple calculations. So from table 7.1, we have used the simple Nusselt number correlations, and we got the Nusselt number is 128, and from the complex correlation we got the Nusselt number is 124. So this is not a lot difference, but it is actually 3% higher than the values which we obtained from the complex correlations. But still, what I got from the theory is that the correlations from the church seals is more accurate, so we can use that one. But if you still use the simple correlations, so I see nothing wrong with this. So choice is yours, you can use any correlations. So that's all. So let's have a quick review what we did. We calculated the surface area, we calculated the heat transfer coefficient. So to get the heat transfer coefficient, at first we did some calculation for Nusselt number. For Nusselt number, we calculated the Reynolds number, and the rest of the thing is as usual what we are doing so far. So that's all.